David Lundweiler, and the title there is a very long sentence because it's on the prospects and challenges of weather and climate modeling at convection resolving resolution. To my opinion, it's trying to make complex thoughts and views a little bit more easier to understand. Please give David a warm welcoming applause and let's kick off.
All right. Welcome also from my side. Whoa, it's really terrifying to stand here, so please excuse me. I'm extremely nervous, but you've probably heard this a few times now. Before I begin, I would like to thank a lot of people. So first of all the volunteers that make this conference possible. It's been amazing so far. I've seen so many interesting talks. I've had so many interesting discussions. And second of all, I would like to thank my co-authors for this talk. They're my team. I work with them on a daily basis. But for this talk in particular, I would like to thank Christoph Scher, Oliver Fuhrer, and Hannes Vogt, who contributed some slides, which allowed me to stay a few days in the last week with my family instead of preparing slides. So who am I? My name is David. I'm an atmospheric scientist by training. I currently work at ETH in Zurich, and they're in a group which is interested in the summer climate over Europe. And I work on the interface between atmospheric science, so climate modeling, computational science, and computer science. So this is basically the summary slide from the first half of the last talk. So the climate system is warming, that is unequivocal, and the human influence on the climate system is clear. So now that we've established that the climate is warming in the last talk, it's time to go a bit beyond and look what's coming in the future. So we know the climate system is warming, and we're very interested in how a future world might look like. But then at the same time, there's this famous saying, making prediction is hard, especially about the future. And one way to do that is by using numerical models, so trying to put the Earth system into equation and use climate models to make projections. But we make our models to answer very specific questions or test very specific hypotheses. And we don't want to create the Earth in a virtual world. So this is kind of important to remember. So all the models are wrong, but some models are useful, especially if you have the right questions. So this is another summary slide from the last talks. It's this very famous IPCC slide from the summary for policymakers, and essentially tells us that we have a choice. Depending on the amount of carbon emissions, we can either live in a world which has a temperature change, like the plot on the left, or we can keep a business as usual scenario, and we can live in a world that looks a bit more like the world on the right. So this is a plot of surface temperature change, and it contains a lot of the very useful, robust features that have been addressed and investigated in the past. For instance, we see that the continents are warming faster than the ocean. We can see that the poles are warming faster than the tropics. And everywhere we have these strange black dots is where all the models that contributed to this plot agree in sign and where the signal to noise is very high. So another way to look at it is by looking at the global mean temperature change. So on the bottom panel you see past observations, and in the big panel we again look at the scenarios. So we have a business as usual scenario on the top, and we have a mitigation scenario on the bottom. This would be roughly the 2-degree world I showed you before. And in the straight red line, you can see the mean change predicted by a large number of models. I think it's around 40. And the color shading indicates the range these models span. So this is kind of the uncertainty range that our models project. And a lot of effort has been made in the past to understand this range, to try to see where this range comes from. And of course, we would also like to reduce that uncertainty range so we know a bit better where we're heading. And in this talk, I want to look at some ideas how we can, we think we can reduce this range by improving our climate models, because we think that a large part of these uncertainties is due to uncertainties in the response of clouds. And if we improve the representation of clouds, we might be able to reduce these uncertainties. So kind of an outline, I first would like to talk about clouds and climate sensitivity. Then I have to give you a very brief introduction into weather and climate models, how they work in a nutshell. Then I would like to talk a bit about new climate models which are able to mitigate, work around some of the uncertainties that are in the current generation of models. Then I would like to talk a bit about challenges in computing weather and climate, so computing these new models. And finally, I want to give a short outlook on what we can expect in the next 5 years, or the next couple of years. So let's begin with the clouds. You remember that I told you that a lot of the uncertainties comes from the representation of clouds. And clouds can react to warming in various ways. And here I've selected a few. So the clouds can either contribute to the warming that would be a positive feedback. So as the temperature gets warmer, their contribution makes the climate system even warmer. But they can also have an opposite effect. And they can moderate the warming. That doesn't mean at all that the climate will get cooler, but that the increase will be a little bit smaller. So, for instance, in a future world, we could have more high clouds, and that would then contribute to a positive feedback. We could have more low clouds, which would have the opposite effect. The clouds could get higher, which would again have a positive feedback. They could get less icy and more watery, which would have a negative feedback. Or they could change their position. For instance, if they move closer towards the poles, this could again have a positive feedback. So you can see that we have a whole zoo of ways that clouds can react. And here I've chosen just a few, so there are more of them. And our problem in the current generation of climate models is that clouds are not explicitly resolved, but we parameterize them. So it means we use physically based, semi-empirical models to represent them in climate models. And the way to illustrate is this. So we have a model world, and we can change that world. And one way you can change it is you can try to simplify it, to make it easier to understand. And here, what the authors have done, they've stripped the Earth of all the continents. So now you have only an Earth consisting of water and an ocean. But nevertheless, these planets, they have features that are very similar to our climate system. So we can see there is an intertropical convergence zone, there are Hadley cells, there are extratropical cyclones. But in essence, the system you have to investigate is much easier to understand. And now you have this idealized world, and you can run it for a couple of years, and then you can warm the entire system by 4 degrees, and it will be up here, and you can run it again for a couple of years, and then you can take the difference between these two simulations, and this is what is plotted here, and is plotted for 4 different models. And you can see that these 4 different models here in the vertical, they react very differently. So the change in cloud radiative effects, the patterns look different. And the change in precipitation also looks different. So, and our hypothesis is that these differences are mostly because clouds are not represented explicitly, and that the parameterizations involved here have a substantial amount of uncertainty. So to explain quickly what a parameterization is, I want to give a very short introduction into what climate models are. So what does a climate model do? It has two important jobs. The first job is it distributes heat horizontally. So we have differential heating around in the tropics. The Earth is warmer than at the poles. And the first job is to kind of mix these two states. And the way it does this is the following. So this is a high-resolution simulation at 13 kilometers, which was, the animation is by Oliver Stepper. And this is basically now how a climate model looks like from the top. So this is not the satellite picture, this is an entirely virtual world. And you can see that we have many of the features. So here, for instance, the tropic, we have the strong convection, the deep thunderstorms going on. Here in the extratropics, we have the extratropical cyclones, so that the low pressure system coming towards Europe. Many of you know these very well. At some points, we will see tropical storms. So here would be a tropical storm. And it is a lot kind of these eddies then mix the heat, the gradient between the tropics and the poles. So this is one job. The other job is to mix in the vertical. You know this, a similar plot from the last talk. So in a greenhouse atmosphere, the atmosphere warms the Earth's surface. And somehow, a lot of the energy from the surface has to get back in the atmosphere. And usually this work goes through the water phase, so through clouds. But still, these clouds are very badly represented. So we have one heat, energy, and mass transport, which has been represented very well since the 70s. So these are Manabe and Smakarinsky and these people. They've done an awesome job. But on the vertical transport, we're still a bit unsure. So, some equations. What the climate model does, it basically solves a number of coupled differential equations. So it doesn't matter too much what this is, but here on top you can, for instance, see the Navier-Stokes equations. Some might recognize this below here, so it's the equation of state or the ideal gas law. And this is from the atmospheric part of a climate model. This is the climate model Cosmo, which I'm using. It is, amongst other things, also used by the German Weather Service to do weather prediction. And now, unfortunately, so we want to solve these equations so we get the nice motions you saw in the animation, right? And sadly, we don't know an analytic solution to these equations. So our only way is to solve them numerically, using numerical methods on a grid. And this is very, very expensive. So we have a numerical mesh surrounding the Earth in 3 dimensions, and we solve the set of 5 equations at each grid point. And then once we solve the equations everywhere, we have a new state, and from that we can then progress in time. So we do kind of the classical time-stepping approach. So now, depending on the computational power you have available, you can vary the number of grid points you throw at the problem, or you can vary the resolution of the grid. And now you will have processes which will be very well represented on that grid, and you have processes which are either not representable or which have a length scale that is too small to be represented on that grid. So typical global climate simulations today have a grid spacing between 125 kilometers. So imagine you have these 2 grid points here, and you have a process that falls right in between. That's then hard to capture by the grid. So we have resolved processes, and we have so-called subgrid scale processes, and from there we have a lot. So we have, for instance, chemistry, cloud microphysics, radiation, sensible and latent heat fluxes, which are very hard to represent on a grid. And then we have some processes which we add as new model modules. So we have, for instance, a surface model, an ocean model, which also has a similar kind of set of equations. And then we have a lot of processes that have length scales which are too small to be represented on the grid, which is, for instance, here, the deep convection and the shallow convection, so the big thunderstorms in the tropics or even in the extratropics. And next, I would like a bit to look at that in a bit more detail. So here we have a very, very wonderful photograph of a thunderstorm over Lake Constance. This was in April 2006, and it's a very beautiful image because we can see a lot of the processes that are going on. So for instance, here we have the up and downdrafts region, so where the air parcels rise very fast with up to 10 meters per second. Over here we have what we know as the anvil region, so there's a lot of ice in there. And here directly below we see something very interesting. This is namely kind of the hydrometeors falling out of the cloud and then forming these gust fronts near the ground. And the fact why we actually can see them in this image is because for this case here, they consist mostly of ice particles. Normally this is rain, and the ice particles makes them capturable by a camera. So now imagine we want to resolve this in a model. So we overlay a grid, and the grid now has a grid spacing of 10 kilometers. So we have information at these grid points, right? And at these grid points. And now what the physical parameterization tries to do, it tries to capture all the processes that are going here in between. And this is an extremely difficult task, and it has been worked on since the 70s, and some of the most brilliant scientists I know have worked on this problem, and we still, even today, have the uncertainties that I've shown you. So we're proposing to take another route, maybe a simpler route. We propose to simply increase the resolution of the grid, because now we have a few points representing the cloud, and we actually can start to resolve the motions associated with these processes. We can go even a bit further and then very well capture many of the features of this cloud. So we've done this. As I said, we use the Cosmo weather and climate model, and we've done this for a simulation over Europe. So we have done 3 simulations, one at 50 kilometer, one at 12 kilometer, and one at 2 kilometer. And we were able to do this 2 kilometer simulation because we use a very special version of Cosmo, which is a version which is able to make use of the capabilities of GPU accelerators. This was an effort led by Oliver Futter. And we used then this model to run a simulation which has about 1500 times 1500 times 60 grid points, and we simulated a period of about 10 years on 144 nodes. We can run 1 year of simulation in about 2.5 days of real time because of this GPU prototype. So I can now show you a lot of statistics, but this is boring, so I'll show you a few cases from this. So some of you might remember this storm. It was Kirill, and it was a very strong windstorm that affected Germany in January 2007. And in this representation here, the white shading indicates clouds, the colored shading indicates precipitation, with the blue colors having rather light precipitation, and the red colors having a bit stronger precipitation. And just to orient yourself, the wind basically blows along these white lines. And now at this point in time, the storm is located here over northern Germany, and it exposes all the typical features of extratropical storms. Namely, here is a very nice warm front with precipitation along the front, and here we can see a lot of a cold front with a bit of precipitation along the cold front. So we have usually precipitation up to 5 millimeters per hour. Now, we can increase the resolution of this model. What you can see is, first of all, we get a lot more detail, but then we get also a bit more precipitation here along the cold front. But kind of qualitatively, the two simulations still look a bit the same. Now, we're trying to disable this convection, this parameterization of deep convection, and increase the grid spacing of the model to about 2 kilometers. And what you can see is that the picture changes quite dramatically. So we have physical features going on which we couldn't identify before. For instance, here you can see these very narrow bands of rather intense precipitation. So these are cold frontal rain bands. And if you, for instance, look closely, it's really fascinating. So the wind blows here along these white lines, and the rain bands are actually not perpendicular to them, but are oriented in an oblique angle. And you can also see that they're a bit broken up. And if you compare this, for instance, to this radar image of which was captured of an extratropical cyclone over the Pacific, you can see that now actually these models start to look like the observations. So if you compare again these two, this looks like a lot more like the observations. Okay, switching seasons, going to the summer now. The same kind of plot, and we're looking now at the day in July 2006. So we have thunderstorms and rain showers in summer. And on the left side, you can again see the 12-kilometer simulation. And on the right side, you can see the 2-kilometer simulation where we treat the thunderstorms explicitly by the equations of motion. And on the left side, all the rain that you see comes out of these parametrizations. So if you, for instance, now focus a bit on the left side and you focus on the precipitation, you can see that it covers very wide areas and that we have mostly greenish and bluish colors appearing. And if we watch closely, you can see that it peaks around noon. So now, around 12 o'clock. Now let's switch to the right side. Of course, the animation has now ended. We can actually now identify the individual bubbles, so we can see the individual thunderstorms in the simulation because they're treated explicitly. And some of the thunderstorms, they have very small areas of very intense precipitation. And this is a very different physical behavior of these simulations. And if you look when the rain peaks, you can see that it peaks right about now. So in the afternoon. And if you think back, when do you experience thunderstorms in summer? It's usually in the late afternoon. It's usually in the beginning of the night. So now the timing of these of the precipitation in these simulations agrees much better. So as a summary for the first part, we want to switch off the parameterization of deep convection, because then we can formulate our models much closer to physical first principles. This yields an improved representation of summer convection and precipitation extremes. This has been very well investigated, so here you can see a couple of papers on that. But the downside is these models are computationally extremely expensive. In fact, if you want to double the resolution of a climate model, you need about a factor 8 in computational effort. So to go from the 10-kilometer range to the 10-kilometer range, we need to somehow find a factor 10,000 in computational effort. And I'd like to show a bit what we've tried in this direction. So computing climate models is extremely expensive, and the way we do it is we use what we call supercomputers. So what makes a supercomputer super is the network. So we have a bunch of nodes, we have a bunch of sockets that are occupied either by CPUs or GPUs or whatever, but the important part is that they're networked together with a very strong and fast network. And then we can slice our problem into smaller chunks and distribute them to the individual, what we call them nodes, so yeah, CPUs or GPUs. And this is the computer I'm using. It's called PIT-Staint. It's located in Lugano at the supercomputing center there. And it consists of about 5,300 hybrid nodes. So each node contains an Intel Haswell multi-core CPU and an NVIDIA Tesla GPU. And it is one of the larger machines of this world. So some might know the top 500 list. So currently it's number 3. And what's more important is that it is also one of the greenest computers in the world. So if you measure, for instance, CO2 footprint. So it is a user machine. So to gain access, you basically write a proposal, and which then gets sent into review. And if the judges like you get some compute time on it. But the important part is that 90% of the compute power of this machine comes from hybrid nodes. So they contain CPUs and GPUs. And we think that the GPUs are chips which are very suited to compute weather and climate models. And this is because graphics cards, so graphics processing units or GPU accelerators, whatever you like to call them, they're substantially parallel and they're throughput oriented. But more importantly, they provide a much higher memory bandwidth, and they're able to hide some of the memory access latency between a lot of threads. And this is important for weather and climate models because, in fact, many of the operations in these models are limited by memory bandwidth and not by the available flops, so not by the available floating point operations. Just to quickly explain what I mean by memory bandwidth, we look at one of these operations we do in the most expensive parts of the climate model, so in the dynamical core, and in there many operations are characterized by the fact that they need information from their neighbors. So to update the grid point here, the orange grid point, we need data from the neighbor on the left and the neighbor on the right for this easy case here. And if we write it down, you can see here that we have A of I plus 1, and then A of I, and then A of I minus 1. And so we have to transfer a lot of data to update the single grid point. And the way to express it is the arithmetic intensity. So it says how many flops we can do, or how much data we need to do a flop. And the easiest way to assess how much is by simply counting. So we can count all the floating point operations here. 1, 2, 3, 4, 5. So we have 5 flops. And then we count all the data accesses, which is 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 times 8 byte in single precision. So we have about, we do about 0.1 flops per transferred byte. Now we want to know whether we're memory or flops limited, and for that we use a very simple analytical model which was established by Williams et al. from Berkeley. It's very insightful because it essentially says that the attainable double point floating point performance can be separated into 2 regimes. So one is limited by flops and the other one is limited by memory bandwidth. So if our arithmetic intensity is above 1, if we do more flops than per byte, we're in this regimes here, and we're limited by the peak floating point performance. Or if we do if the arithmetic intensity is low, we're here in the memory bandwidth bound regime. And now we can go back and look at our 0.1 flops per byte, and we find that we're here on the left side of the curve. And this is typical for these stencil operations, which we find in the dynamical cores of weather and climate models. Now, if we increase the memory bandwidth available, of course, our time to solution will go down. And this is why we think GPUs are good for our models. So we ported our entire code. The entire thing is very well documented here in this paper by Ollie. And so Cosmo is about 300,000 lines of Fortran code. The dynamics, so that the part treating the equations that I've shown you were rewritten in C++, and we use a domain-specific language that some of us wrote called Stella. Stella is nice because it abstracts the hardware architectures from the operations. So we have backends now for multi-core and GPUs, so written in CUDA. And it allows us very low-level aggressive performance optimizations, whilst, so for instance, changing the loop order, while still maintaining a higher syntax, the same syntax at a higher level of the code. The physics were ported using compiler directives, so I was personally more involved in this part. But the essential thing is that after about 10 person-years of work, we had the entire time-stepping algorithm ported and validated. And this now avoids expensive data movements between CPU and GPU each time step. So what did we gain from using this new architecture? And one way to look at it is through a strong scaling experiment. So we take a given experiment, a given problem, which is in our case just a given domain size, and then we throw an increasing amount of resources at the problem. And what we expect is the time to solution to go down proportionally with the number of nodes we throw at the problem. So this is what we show here. So on the y-axis you have time per time step, which is a measure for time to solution. And on the x-axis you have, when you go to the your right, we decrease the amount of nodes, or we increase the amount of grid points we compute per node. So again, here you can see two regimes. Here on your right, you can see the linear scaling regime. So here, the time to solution decreases about proportionally with the resources you throw at the problem. But then down here, we see a saturation regime, and this can be mostly understood, I think, by Little's law for those who are interested. So now what do we gain? So here at the point where we think we're optimal, we gain about a factor 6 in time to solution, or what's even more important for us, we gain about a factor 8 in resources. So now we have a very nice and efficient model, and the question is now, how far can we push this? I've shown you regional simulations over Europe, but actually the problem of climate sensitivity, so the uncertainty range I showed you at the beginning, is a global phenomenon, and we wanted to know how far we can get. So we now do the other part. We do so-called weak scaling of the problem. And by weak scaling, we mean that we vary the number of nodes. No, let me begin again. We vary the size of our computational domain, and we vary the nodes we throw at the problem proportionally. So what we expect is the time to solution to be constant. And this is not a given, but in essence it means that for this experiment here, where we simulated over the Alpine arc, we use about 10 nodes. For a European domain, I've showed you before, we use about 100 nodes. And the question now is, will this entire model scale to the planet? So that would be something around 5,000 nodes. And now the question we want to answer is, first, does it scale? Second, what's the time to solution? So are we there? And we want to establish a baseline at 1 kilometer. And finally, we want to assess the efficiency of the Cosmo model. So we did this entire exercise, and we find now we again here have the time per time step on the y-axis, which is a measure for the time to solution. And here we have the number of nodes to the entire size of the machine, which is about 5,000 nodes. And we can see that the time to solution actually stays constant. And that's what we expected due to the numerics that are in the dynamical core. So, okay, we now have a model that can scale at very high resolutions to global domains, and we can do some experiments with it. For instance, we can test whether we're fast enough to do global simulations. So to this end, we did an experiment of the idealized baroclinic wave. It's a very famous test case for climate models. It's by Jablonowski and Williamson from 2006. And we simulate the evolution of a baroclinic wave. And the baroclinic wave, essentially, you can think of it as the extratropical cyclones I've showed you before, and what you know kind of as autumn storms. And because we have a regional model, we now need to apply some tricks. For instance, we glued in the west-east direction, we made the domain periodic, so we glued them together. And we have a small problem at the poles. Namely, because we have a regional model here, you can see that the distance in the grid gets very, very small. So we get at the pole, ultimately we get a singularity. And we have to address this, so what we do is we simply cut the domain at 80 degrees south and north, because here we do a computational experiment. But we nevertheless, we cover about 98.4% of the Earth's surface, so this is simply the sine of 80. And we then use the setup to do a simulation which is about 10 days long. And here we come to the solution of after 10 days. So here you can see this the baroclinic wave after 10 days. So we can see 3 low pressure systems following each other. And then in one of the low pressure systems, we can see here this cold front, or here the cold front, which gets wrapped around the core of the low pressure system. And if you look closely, we can see these very funny things here. These are small eddies which are embedded into the mean flow. So here we have a zoom of the small eddy. And this is actually a new feature. So this case has been run over and over by hundreds of groups, not hundreds, but by a lot of groups, but only at grid spacings of 20 or so kilometers. Now that we can go to 1 kilometer, we actually find new phenomena in very established and old cases. Okay, now coming to the time to solution. So when we do climate simulations, you can do a lot of experiments, but 2 very famous ones, or 2 that you do a lot, is the first one is you do a 30-year-long time slice experiment. So you can, for instance, simulate the last 30 years until today, and then you can simulate 30 years at the end of the century, so for instance 2070 until 2100, and then compare the 2. So this is a very famous type of experiment. The other one would be kind of century scale simulations, where you simulate hundreds of years. And of course, to do century scale simulations, you would then need to be about 10 times faster. So to do these 30-year-long simulations, you need to be able to simulate a few months per day. And if we now go to our benchmarks, we can see that here the 0.23 SYPD, so this is simulated years per day. So these are a few months, and we can reach that today at the grid spacing of about 2 kilometers. When we scale to the full machine, at 1 kilometer we need about another factor 5 to 7 to get to this window, and of course to these century scale simulations we need another factor 10 to do century scale simulations at 1 kilometer. So we have a big challenge to go, and of course these simulations come at a cost. And we measured the power they required, so the energy in megawatts per simulation year, and then extrapolated from there to the 30-year-long simulation. And you can see that, for instance, at 1 kilometer we use about 18 gigawatt hours. And you can then, using the carbon intensity of the Swiss energy mix, you can then convert this into a CO2 solution, which would here be for a 1 kilometer simulation would be about 3,200 tons of CO2 equivalent. Just to compare, this annual footprint of a person is between 0.1 and 10 tons of CO2, depending where you live on the Earth and, of course, on your lifestyle. So we have a big number here that we have to bring down. We have a lot of ways how we try to do that. So we can look at the energy mix, we can look at the arithmetics or the algorithms in the model, we can look at the math, we can look at compilers, we can look at the computer architectures, we can look at the chip architectures. So there are a lot of questions still open and a lot of potential to address these problems. But nevertheless, we can also say that we can do global simulations with 2 kilometer resolution. So the nice animations I showed you, they also apply. But we wanted to establish a baseline, and we wanted to know how efficient we are on today's computers. And to this end, we propose to use a new metric, which is called the memory usage efficiency. And it draws from two main ideas. The first idea is that if you're limited by memory bandwidth, of course, you have to get as close as possible to that upper bound that I showed you from the roofline model. So the first term in this metric is the measured bandwidth, so what you measure during execution of your model, and then in the denominator we have the achievable bandwidth, and we can get that through a set of highly optimized micro benchmarks. Then the other idea is that you've maybe heard of the expression floating points are free, and this comes from the fact that floating point operations on today's architectures, they're actually much cheaper than data movements. So they're actually about 1,000 times cheaper in terms of time, 100 times in terms of time, and about 1,000 times in terms of energy. So that's been measured a few years ago by John Scholf. So that the second idea is that in order to reduce the energy, so this factor 1,000 here, we have to reduce the overall amount of data transfers, and we can simply count the number of data transfers we do in our model, but then comes the hard part. We have to know the lower bound. So how many transfers are actually needed? And to this end, Torsten, Carlos, and Greg developed a performance model. It's a bit hard to explain in 2 minutes, but in essence, what it does is you have an operation, as the one I showed you before, and then you look at what data do you require for that operation, and what do you write out. And then you map these data requirements, you map to your architecture, so for instance, to the different cache levels, and now then you can compare it to what you actually do. And now the important part is this performance model doesn't only look at one individual operation at a time, but the important is if you do an operation, it will have predecessors and it will have followers. So they can share data and they can share data. And their performance model looks at the algorithm or the implementation of the algorithm, how it is written out, and then gives us a lower bound of the required data transfers. So we obtained that for our model. The number itself is a bit non-telling, non-informative, but we can see that we perform quite well. So for the first term, so it means that our implementation fits the GPU architecture quite well, but we can maybe do a bit better with regard to the memory bandwidth. And now we hope that other groups will take up this measure and compare so we can learn from each other. All right, that was mostly it. Here are my conclusions. I hope that I was able to show to you that we have some very interesting, cool, fun physics to address, and that we have some very interesting computational science problems to solve if we want to attack these big questions, such as the climate sensitivity. And there is a lot of potential for improvement, and there's a lot of interesting science to be done, and I hope maybe some of you would be interested and talk to me or tell me that everything I've done is wrong and that you could do it, all of it, much more easily, and that would be amazing. So thanks a lot for your attention.
Thank you very much for this really fantastic view on how you do your work. I can understand that some people are quite jealous about the computer power he's using, isn't it? No? Some questions, please.
Just maybe one moment, sorry. If you want to post questions in German, that's totally okay. We'll then try and translate them into English so everybody can understand. So if you want to ask in German, go ahead.
All right.
Okay. Hello. Okay. Thank you for the excellent talk. Did you ever try to dynamically adapt the grid size like it is done in mechanical engineering to make it more precise? Or is that not possible in that case?
We ourselves didn't do it. We had another task, but it is a very active research topic in my community. So much less in climate, but a bit more in weather prediction, because there you have to be even more efficient than we are in climate. And what you can, for instance, do is, let's say you're interested in tropical cyclones, in hurricanes, and whenever you detect a cyclone, a hurricane, you can dynamically adjust your grid. For climate, this is a bit less interesting, in my personal opinion, because the energy balance of the oceans is mostly governed by these low-level, very shallow clouds. And to resolve those clouds, you need a grid spacing around 1 kilometer and below. So if you want to cover these clouds, you need an extremely high resolution everywhere anyway. So maybe we should focus on that first before we go into these refinements.
Thank you.
Can I have a question from the web?
There are no questions.
Okay, lots of others here. Number 2, please.
Would observing the clouds help with describing them or simulating them, like flying there with aircrafts or UAVs or something like that?
Yeah, we do that a lot, not me personally. There are a lot of measurement campaigns, the people flying through clouds with aircrafts, people trying to model each of the processes of how cloud drops form, how they grow, how they collect each other. And there are, since actually decades, we do observation campaigns. So one of the most interesting ones that will happen, it's maybe right now or in a few months, is the Narwhal 2 campaign. Is involved is also the Max Planck Institute in Hamburg, and they will do some very interesting coupling. They will do some very interesting new experiments, but at the same time they will also apply these high resolution 1 kilometer or below models at the same time and try to leverage the knowledge gained from both of these fields. So yeah, we do it, and of course we also use satellites. There's a lot of observation of clouds, but the problem is extremely hard.
Good, number 7.
So I'm from a somewhat different field. I used to do some medical imaging stuff on GPU, and I was rather surprised when you said that the memory bandwidth was the most decisive thing about your usage of GPUs, which is really unusual because you usually use that for great computational density per byte. So is that mostly about, I don't know, having access to cheap, really fast memory at a large scale? Or have there been like attempts to develop ASICs, that is application-specific hardware for your kind of computations, climate modeling?
Well, the application, why we use them really depends on the characteristics of your application. And you remember the roofline model, right? And you can see that the increase in kind of the difference between the two lines was about as big for the increase in memory bandwidth than the increase in peak performance. But it's a very different view you have, of course, because I guess you do a lot of matrix multiplies and these operations, but they're actually useful for both types of problems. Now, I mean, why they were chosen, I don't know. Well, I know, but I wasn't the person that made the decision. This was the CSES, and they did a very thorough analysis. But one reason is that to build supercomputers, you usually can leverage what is there in the consumer market, right? You can essentially leverage what is already out there and try to put it together in a new way. Rolling your own chip, I've seen that there is a talk about that, is very expensive. But nevertheless, there have been attempts using, for instance, FPGAs to try and co-design codes and chips. And this is something that we will certainly have to look at in the future. but it has not been done yet operationally. So the people I was talking with, Donofrio et al. from Berkeley, there are some very interesting papers on that.
We have enough time for questions, David. I see some other people. Number 3, please.
Thanks for the very interesting talk. Currently, clouds or radiative transfer is modeled in 2D. Do you also plan to experiment with 3D radiative transfer, like the 10-stream algorithm or something similar?
Yeah, well, right now our radiative transfer code is the Delta 2 stream approach. It is a bit a question on the processes you're interested in, right? If you're interested in a very timely, high-resolved radiative transfer question, you of course want to go there. But radiative transfer is the other expensive part in a model. So it's on one case, it's the dynamics, and then the next one is radiative transfer. And actually today we don't run radiative transfer every time step, but we currently run it in the 2-kilometer model about every quarter of an hour. And we think it's just enough not to affect the results of our simulations too much. So first we'd have I would like to increase the frequency we call that module before going to 3D radiative transfer. But yeah, it's a trade-off. And currently we think it's okay still. But if you want to go to 1 meter LES, there is a lot of work, for instance, using also ray tracing and these ideas. There's a lot of work going on in the community.
Okay, we still have 10 minutes. I see a question on the web. Yes?
Yes.
Great.
The Fortran code you were talking about has been around for quite a few years. What about the parallelization code if the architecture changes?
Okay. So you have a number of ways you can approach this porting problem, right? And this depends a lot on the politics going on in your community. What is this community trying to be, and where does it try to go? So for instance, there is one idea that in order to port large scientific codes to different architectures, you have kind of the master branch of your code, and you try to keep that as clean, as nice, as well tested as possible. And then whenever a new architecture comes around, you simply take that code, you branch it off, you let a shitload of PhD students on it that port it, and then you have a new code. The other approach is what we were trying to do. So Cosmo is what we call a community or a consortium model. So it's about, I think about 15 weather services around the world that want to use it. It's about more than 160 universities, and I don't know how many individuals from the top of my head. So they all have different machines. They all have different architectures. And we chose a way where we try, or Ollie did, he's the mastermind, a way that we try to contain the single syntax at a high level. So we want to make a minimal amount of changes between architectures. So this is why they use this Stella. They developed the Stella library in order to make low-level optimizations to the code. And that's also, then we use the compiler directive, which we're supposed to be able to not change the code that much. In practice, this is not possible for every small detail, but for large parts of the code. So there are these two approaches, and just to tell you, if you're interested about it, here is a list of literature, and I think this paper describes it in detail.
Take something to drink. I have a couple of questions still. We have some time. Number 8, please. You're in the back. Sorry, we can't see you really, though.
Thank you for the talk. You stated that most of your calculations were for climate models. Do you think it feasible to apply these to operational short-time weather models?
Okay, so to develop that GPU version was actually a lot of it was driven by Meteo Swiss, which is the Swiss weather service. And a lot of the developers were paid by Meteo Swiss. And the initiative, I think, a bit of it was also born there. Because today, they run this code that I showed you the Barraclinic wavefrom. They run that operationally. They do, I think, around 32 kilometer simulations and one kilometer simulation operationally daily. And currently the code is reintegrated into the master branch, and I know that several other weather services want to pick it up, because for them it's much less about large domains, but for them it's about the energy use. So by switching your architecture, you save a lot of energy, and if you have to pay the energy bill yourself, the investment into the engineers will be compensated quite fast.
Number 4 in the back.
Yes, thank you. I have 4 questions. First, 4, yes. Firstly,
Start with 1.
yes. First, the time to resolution seems to be very high. What's the practical limit in that? And secondly, what's the main time between failures for a machine like the ones you run? And the third question, what's the minimum resolution that you expect to be useful? Will there be a qualitative plateau eventually? And fourthly, and this is a little different, how about the competition between models and the parametrization? How much does politics play a role in that? I mean, in the sense of international politics and the competition between different climate models coming from different nation states.
Okay, I will answer the first 3. The last one will take a long time. We can talk about that in between. So,
Yes, just 3 minutes.
Yeah, minimum time to solution. So it is the latency of an architecture. So the latency of the memory access. So there will be some physical limits on how fast you can access a memory. So that's why we think it will be very hard to go to 10 or 20 simulation years per day, because today we apparently can't see an architecture that the latency is short enough. The second question, what was it? Can you help me again?
Are you still there? Yeah.
Yes. What's the mean time between failures for a supercomputer?
I don't know the number from the top of my head. From my experience from doing these simulations is, I would say, each month. So we did this in monthly chunks, and I would say it was about 10%, and it was mostly disk access that failed. Meteo Swiss has 2 computers, so whenever one fails, they switch over the entire thing to another one, so they have backup systems. I don't know in percent, but I think they're very robust. And the third question was again?
Third.
Sorry, I'm so nervous, I can't remember.
Qualitative plateau in resolution?
Yeah, so the ultimate resolution that we want to go through to is 10 to the minus 2 meters, so 0.1 centimeter, because that's kind of the inertial sub-range of turbulence.
I see a nice crowd arriving here, and meanwhile we have a question at number 5. I'm sorry.
Cool intervention.
Thank you for the talk.
Welcome. We're having a roll.
Thank you for the talk. So my question is on the grid size. So with smaller grid size, you have to decrease the time stepping as well. And you're using a weather model, as far as I understand, to do climate modeling. So now your problem is that the time stepping is getting small and your numerical errors add up. And in fact, if you do that over 30 years, your results will be some kind of full of numerical errors. So why not do a very good simulation for 1 year, do a parameterization and use that parameterization for the climate models again, and do adaptive grid blah blah there.
That's a nice question. Thank you.
Okay.
Sir.
Do we have enough time? Can I try to
1
answer?
minute. Is that
1
okay?
minute?
2 minutes?
Okay, yeah.
1 minute. In 1 minute.
So-
We will solve it all.
So in numerical schemes, you have explicit schemes and you have implicit schemes. And in the explicit schemes, yes, you have to decrease your time step with the grid spacing, but the cool thing is that the methods are only local. So the perfect linear scaling that I showed you is because the methods only involve local communication, and many implicit methods have global communication. So if you think of it in terms of the energy question again, the energy consumption is a lot higher. Then coming to the numerical errors, of course the numerical error is given by the grid spacing and a bit less by the small time steps. Because, first of all, we have a lot of forcing. We have the sun, which is a very strong forcing. We have continents that force. We have mountains that impose forcing. We have very large dynamical systems that impose forcing. So the forcing, when you compare the strong forcing with the error, the forcing will dominate. Then the other thing is that we have something called a chaotic system. So the Lorentz papers, if you know what I'm talking about. So very small errors can cause very large differences in the simulation after a couple of days. And we have, by now we have some methods how to address this chaos problem, which the solution is we do a lot of simulation and perturb them a bit. So in the end, they will have a climate which is in the mean very similar, but the initial state, the state at a certain time step is very different from each other. So this is a lot of work by Tim Palmer and his group. If you're interested, I can recommend some papers on that.
Well, David, thank you very much for this fantastic lecture. We're glad to have you there to take a look at how this is changing.